Even like I worked on the
I'm like not
yeah, obviously he could write down the.
I don't be honest. But I don't know if I should be with the video.
but like I think you better
It's basically
no, it was like
kind of to what I was asking.
I know. See,
kind of you need to be how
basic.
I wasn't sure.
Remember
I didn't.
Oh, right.
Yeah, you can. Yeah, it's like
exams come and go. Like, this is my first ever.
Oh yeah, that's like.
But this is my first hello guys. But this is not my Oh, I think in my heart.
So before we have our official introduction, I want to present our visitor with two copies of two editions of Jewel in the Crown. This was the original 75th anniversary volume, and this was the 90th anniversary supplement. And all of the students here are going to be helping us write the 100. Yeah. You know, some of the things you're experiencing in your classes, those are really good materials for the 100th anniversary supplement. So start working on it. So anyway, welcome.
Thanks a lot. I will come again for the 100th one, I guess.
Good, thank you. So yeah, today we have Carlos Errando letters in your just body of pronunciation for American English. So Carlos got his master's in Valencia, Spain, and education, right?
So in electrical engineering.
In engineering, right. Yeah. And then you went to KTH for your PhD.
Right.
And working in integrated optics there, you got your very prestigious Marie Curie Fellowship that allowed you to go to MIT. In 2017 or
That was my PhD.
Yeah. Before you worked in you worked together in that European project for quantum using two-dimensional material, great techniques. And now you are an assistant professor in UDEL, right?
Yeah, well, I just signed my contract last week, but I'm starting there in April.
Congratulations for that. And
thanks.
thank you very much for being today and giving me.
All right. Yeah, thanks a lot for the introduction. And thank you for being one of the only people that pronounces my name properly when they introduce me. It's not very common, and I understand why. It's just a very hard name. So, yes, they have said my name is Herranz. I'm at MIT right now. I'm a postdoc there in the group of Professor Dirk Engelund. Some of you may be familiar with his work. And starting from April, I will be an incoming assistant professor at TU Delft and QTech in the Netherlands. And today I'm going to talk about compilation of work that I have been doing both at KTH in Stockholm during my PhD times, and a short 1-year postdoc that I did also at KTH in Stockholm in Sweden, and this last 2 years in MIT. So the title of my talk is Building Blocks for Large-Scale Classical and Quantum Photonics, and I would like to start by showing you this picture. So this is a picture that I use to usually scare my audience. If you're familiar with free space optics, this looks like a nightmare. It's a great quantum optics experiment from the Max Planck, from the group of Immanuel Bloch. So I'm pretty sure this was working. I'm pretty sure this was also very hard to align for all the PhD students that were working on it, because it does look extremely hard. So you have all these optical components, all these mirrors, all these tools in here that are, of course, very bulky. As you can see them here, this is an optical table. So this is the size of a small bus, basically. This costs a lot of money. It's very unstable. So I'm pretty sure every day the students have to go there and tweak the mirrors to probably spend most of the day doing the alignment to maybe, if they are lucky, do the experiment in the night. So this, as you can imagine, this is not the most scalable system. If you want to make this a little bit more complex, you want to increase the complexity. So what we try to do in the integrated photonics community, and many of you may be aware of it, is to shrink these kind of circuits all the way down into these kind of optical systems all the way down into chips. So we can get larger, more functional optical circuits. So if we look at a generic large-scale integrated photonic system, we think of a chip, and this is a schematic. So we have an integrated photonics chip that has waveguides on it. So these are waveguides with silicon nitride. It doesn't matter the shape of them. In this case, they have a specific shape, but they are waveguides that are basically interconnecting devices inside of this chip. And these devices can be sources, be it like lasers for classical photonics, or quantum sources if you're going to do something with single photons, or quantum memories if you want to do something with storing that information. We want to have detectors also, to again detect your information, again being classical detectors, quantum detectors, or whatever you want to add in there. And then you can have some other components there, depending on your applications. For example, nonlinear optics. There's many people in this room probably that work very heavily with nonlinear optics, very useful components, devices for sensing, and so on, depending on your application. Now, something that I want to point out is this center part in here that connects all these devices, that is the largest in this circuit. This is the reconfigurable circuit, and the key aspect here is reconfigurable. So I'm going to be talking today a lot about reconfigurable photonics. And the reason why you need reconfigurable photonics, and I'm going to expand on that a little bit in the next slides, is that when you make circuits on a chip, on a foundry, or on your clean room, whatever you design and whatever you fabricate are different, and they are not going to come out the same way. And if you would try to make your circuit to do a certain signal processing task or something, it's not going to end up doing what you want it to do. So to do that, what you need to do is to reconfigure your waveguide so that you actually make your chip, adapt your chip to your application. And what we use for that is phase shifters. And these are all these little components that I have added here. These orange components here are phase shifters that just change the phase on a waveguide. If you change the phase, you can actually change phase and amplitude. You put it inside a Mach Zehnder interferometer, and that means that you have full control of all the degrees of freedom within your band. So of course, you want this chip to be fabricated on a wafer scale so that you can have it scalable. You can have a very large chip. And you want to have electronic control to control all these devices inside the chip. And in the end, just go into your computer and tell your chip to do whatever you want from the computer directly. So if we look at a device, actually real life device, not a schematic like what I was showing before. This is from the group of Mark Thompson in Bristol. This is actually a device for quantum optics a few years ago. And it's a large scale integrated photonic circuit. This is a nice picture of the device under the microscope. If you look at the schematic, it looks like this. So you have a lot of waveguides. All these lines here are waveguides. And something that I would like to point your attention to are these components there. these little U-shaped orange components, you see that there are many of them. They make the bulk of the components in here if you don't consider these waveguides as any active components. Those are actually phase shifters. Those are devices to reconfigure the chip. And in this case, they use more than 90 reconfigurable phase shifters to do all these things or some of these things. So they definitely use them to compensate for fabrication variation. Again, when you fabricate the chip, it doesn't come out as you wanted it to come out. So you need to reconfigure your circuit so that it actually ends up doing what you want to do. And what you want to do in this case, for example, is to route the laser light. For example, in here, they have a laser pump that comes in from the outside here. And they need to have this laser split evenly in all of these waveguides in here. So because this tree doesn't come out exactly as they wanted, they're going to have different power distribution along these waveguides. So what they do is to tune all these phase shifters in here to actually tune the amplitudes of the light in these waveguides in here. Same goes for the qubit analysis here. So here they generate qubits. That doesn't matter for us right now. And you want to interfere certain qubits and not other qubits. And you can do this with these phase shifters in this side of the chip. So you can use it for qubit analysis, for quantum gate reconfiguration. And if you design this circuit properly, it can also allow you to do to add redundancy to your circuit. So you can actually make a circuit that is redundant so that if something doesn't come out, doesn't actually work, there's a waveguide that is broken or something, which happens quite often when you get these chips, or some device that just doesn't work, you can actually route around it and live without it if you have a circuit that is reconfigurable enough. This allows you to also do prototyping if you make a circuit that can be reconfigured to do a lot of different things. So you can actually prototype without having to fabricate another circuit, another device. So with this, I want to tell you that phase shifters and reconfigurable photonics are very important for photonics, and you want to have them on the chip. So in this talk, I'm going to be talking about these three aspects, and they're all joined by reconfigurable photonics. So I'm going to be talking a lot about reconfigurable photonics, and I'm going to also be talking about sources, in particular quantum sources, single photon sources. And I will be talking about detectors and how they interface with reconfigurable photonics. And these are also quantum detectors. So I will start from the reconfigurable photonics side of things. So if we look at one of these phase shifters, so this is zoom in here, you just see two beam splitters here, two directional couplers, and there is in these two arms that form an interferometer, there is one phase shifter in one of these arms. So today's phase shifters, if you go to a foundry and tell them, okay, I want to have all these devices, I want to have one phase shifter in each of these arms, they will tell you, okay, your phase shifter is going to be consuming about 30 milliwatts of power, in the tens of milliwatts of power. And that's because they are thermo-optic based. So you have a little heater, a little wire, resistive wire that you would just be throwing a current through, and that's going to heat up your waveguide. It's on top of the waveguide, so it heats up your waveguide, and that changes the refractive index to the thermo-optic coefficient. So that is obviously consuming a lot of power because you have to heat up this whole.
Yeah, how controllable is that process? How precise can you get in temperature? With this.
So, I mean, it's used in very large scales. So it is pretty controllable. I mean, you can have current sources that are very controllable. So that's not a big problem. The controllability problem, which is a good thing that you ask about it, is when you have many of them together. So when you have many of them together and you start wanting to have a phase shift here and a different phase shift here, and you know exactly what you want to have in there, but when you start running them together, they start cross-talking.
Yeah.
And it's very hard to really know the thermal distribution that you're going to have when you have all these things at the same time together. So it's actually a really big problem of thermo-optic phase shifters when you go to large scales, when you really want to pack them together to make something complex enough. By the way, yeah, if anyone has questions, I'm very happy to answer them along the talk. So, all right, so thermo-optic phase shifters, they consume a lot of power, and this is actually starting to be the bottleneck right now for large-scale reconfigurable photonics, or what is called programmable photonics nowadays. So today we have devices that have about in the hundreds of phase shifters. This is one example from actually my group, from the Errando's group, before my time there. So using 170 phase shifters, we are in the hundreds these days. let's say we want to keep increasing this number. We want to make more complex photonics out of these chips. So we want to aim for 1,000 phase shifters. So if we use thermo-optic phase shifters that we're using nowadays, this will consume the same amount of power as half of my laptop right now, which is quite a lot of power if you think about a single chip, 1 centimeter chip dissipating all that power. So you can already see that something that actually people have to do with even 100 is they have to put all these Peltier elements to dissipate as much heat as possible to cool down the chip as it's running. But we want to go farther than this. We want to actually make circuits that are much more complicated with, let's say, 10 times more. So we want to have 10,000 phase shifters in one of these circuits. This is, you can do the math. This is 5 laptops. So it's consuming the same amount of power as 5 laptops, which actually happens to be roughly the same amount of power as 2 fridges of these fridges that you have at your home. If you have put a hand behind your fridge at home, you can already feel the heat that's dissipating. Imagine having that in 1 centimeter square chip. You're going to melt it. I mean, you're not going to do anything with it. So this is a problem, and this is a big problem in the field, that we cannot cram all these phase shifters together. So what we targeted to basically take this number and bring it down by several orders of magnitude in power. So go below 1 microwatt of power. And the way we do that is by using MEMS. So the next slides, I'm going to talk about what MEMS are. So MEMS are microelectromechanical systems, which stands for that. And we use them, of course, in integrated photonics. So if we look at this schematic, we have a mechanical spring that is holding a plate of a parallel plate capacitor. So you just think of it, just the 2 plates of a capacitor, and this spring is holding it, clamping it to some non-movable area here. And this one is clamped here on the bottom also. So this plate cannot move. This one can move with this spring. You apply a voltage, you apply a potential across this capacitor, you get an attractive force. So the equilibrium between that attractive force and the spring force will lead to a certain equilibrium position. So you achieve displacements on chips. And this is something that is very old. I didn't invent this. This is something that's actually in your phones right now. You have all these accelerometers and sensors in your phones that work with these kind of technologies. So you have some sort of lens actuation in there. So this is called electrostatic actuation or capacitive actuation. It's low power because in the end what you have is a capacitor, and you usually run this under DC actuation. So you actually have a capacitor on DC, it consumes basically zero power. You do have leakage powers and so on, but very, very little power, which makes it also cryogenically compatible, which is very interesting for quantum applications. So my group and other groups in the field have developed several MEMS reconfigurable photonic components, such as phase shifters, directional couplers, filters. I'm going to talk about some of them today. And also within the quantum and color center field or quantum dots fields, people have used this strain tuning with MEMS because every time you move something on a chip, you also generate strain in your springs. So you can actually use that to strain to strain some components in the chip, like quantum emitters and memory, so you can actually shift the frequency response of these things. So just for the people not familiar with MEMS, this is a video, and I hope it works, and it does, of large-scale MEMS in action. So this is a microscope video. This is a pretty large circuit. It's not exactly the ones that we use in photonics, but I will show you those in a while. You see this shuttle here, which is the thing that is moving. So this is suspended, kind of floating. It's only held to the rest of the chip through this spring that you see a part of it here. This is basically a thin silicon beam that acts as a spring. It's kind of soft because it's thin. The capacitor that I was showing you before is in this case formed by these fingers. So there's basically these 2 surfaces of this finger versus these fingers is what forms a capacitor in this case. And we have the voltage being applied in between this shuttle and this static area here. You can even see there in the video the steps. Those steps are literally voltage steps that we are applying on a voltage source. So what you see is displacement on a chip. So pretty basic. This is used in this.
How is this suspended? Is it vertical or on chip? Right? It's on.
Yeah, so good question. This is looking at the chip from the top. So it's basically floating like that on top of the chip. So it's suspended in the sense that it's clamped by these springs here. There are other springs that you cannot see here, but it's basically held by flexible springs in place. And yeah, this is in silicon. Yeah. So if we look at one of our devices, this looks a little bit different, but I'm gonna explain you how. So this is start seeing, looks like something more of a photonic device. So we have a waveguide here. This is in silicon. So this is a silicon waveguide that travels through, and this is a ring resonator. So light goes through the waveguide here, couples into the ring, and then but that light will couple out, and the ring at certain wavelengths is going to be resonating in here. So two things that you will notice here, if you're used to seeing ring resonators, there are these weird holes in here, and also there is this other extra waveguide here, or some sort of beam that seems to be a little bit at a different height than this part here. So that the reason for that is because this is actually cantilevered out. These holes, what they allow us in the fabrication process is to remove the oxide underneath the silicon. So this thing is a cantilever. It's standing, floating, and it's only held to the rest of the chip by this area here. This is all clamped, right? So this cantilever surrounding it, what you have is a thin silicon beam, and then you have the waveguide that carries the light on the outside here. So this waveguide, if you know waveguide photonics, this waveguide has evanescent field. So part of the field is sticking out of the waveguide. So we use the fact that we can interact with that evanescent field with this beam outside to actually change the effective mode index of that waveguide. And when we actually apply a voltage here, in this case, between the top, the device layer, the top of this chip and the substrate, we actually can bend this down. And this is how the device actually actuates. So these are the displacements that you can see on the chip. So if we look at how what we measure out of these devices. So in this case, we are looking at the phase shift. And we are translating resonance shifts here into phase shifts. And here's a schematic of actually a simulation of the waveguide evanescent field. As I was saying before, you see the mode sticking out from the waveguide. And as it comes close to this other beam here, it gets pulled out a little bit. There is a change in the geometry of this evanescent field, basically. That results in a change in effective mode index that changes the phase of the wave that travels through the waveguide. So what we see here is this phase changing over voltage. So when we apply a voltage and we start bending this ring, we start changing the phase, and we see how we achieve, in this case, somewhat around pi phase shift. All right. So yeah, this is actually what we actually measure directly from the device. So we see the resonance frequencies shifting as we apply a voltage. So we can shift the resonances from side to side in wavelength, the ring resonances. So of course, the next step of that is like, okay, we have shown that we can make MEMS, we can combine them with photonics. We know that these have very low power. So the whole point of this is to scale up like a programmable photonics, right? So let's go do that. And this we did in a European project called Morphic project. And there was a collaboration with a few universities in Europe and with a foundry. So there's a collaboration with IMEC in Europe, in Belgium. And they have this very nice silicon photonic foundry that you can get very advanced silicon photonic components. So what we did was to design our photonic MEMS in there and then do a post-processing step to under-etch this foundry to suspend the devices, which is something that the foundry usually doesn't do for you. And then test them, of course. So going from wafer scale process and to have MEMS inside this foundry to really target the large scales that we want to demonstrate. So this was one of the devices. This looks like a little bit like the video I was showing you before. So this is again a top view, and you have a waveguide meandering here. This is the main waveguide that we want to, in which we want to introduce a phase shift. This was fabricated in a foundry. So this we got from a foundry and just under-etched. And what we have is this shuttle again, like similar to the one in the video. In this case, it's holding this small beam, silicon beam, here that is very close to the waveguide, so that it can be affected by the evanescent field. And then we have the actuator, so the capacitor is these fingers in here and these fingers on the back here. And again, by applying a voltage in between this shuttle, which is connected here via these springs, again, thin silicon beams, and this static area, we can achieve displacement in this axis that, again, changes the distance, the relative distance between the beam of silicon and the silicon waveguide, and that will introduce a phase shift. So what we see is more than 2 pi phase shift, which 2 pi phase shift is basically what you need to achieve with this, because it's the whole way around the sphere. And very low loss, below 0.5 dB loss, which is actually dominated by the transitions here. It's not actually the device itself what's being so lossy, it's these transitions. With below microwatt power consumption, which is actually key. So if you see this plot here, is as we apply a voltage, we are looking in this case at a few different wide wavelength range, and we see how we introduce a phase shift. So just to summarize this section, so what we showed in here was foundry scale reconfiguration with more than 5 orders of magnitude less power consumption than what we can get nowadays. So this can potentially mean that you can actually, remove that part of the bottleneck, and you can make 5 orders of magnitude larger photonic circuits. In reality, it's not going to be like that because you have a lot of other bottlenecks that will come, but at least you get rid of that first bottleneck, which is very important.
Could you explain again what is the exact mechanism for the phase shift when you're doing MEMS?
Yeah, so I can show you in here. Yeah. So what we do is we are perturbing the waveguide with a block of silicon. So we have a waveguide, which in this case, it's this one here, this mode, and it has a certain evanescent field around it. So when we change the relative distance between this waveguide and this silicon beam, we are changing the effective index of the mode. Right? In this case, we do it vertically. In the case that I was showing with the foundry device, we are doing it horizontally.
And it's in that for a specific polarization, right?
Yeah, well, yeah, this is for a specific mode. Yeah, which in this case, we have this is for a T polarization, T quasi-T mode that you have in these waveguides. You can do the same for quasi-TM modes. You will need to just design it the right way. But we are working here only with quasi-T. Yeah.
Can the strain induced by MEMS be used to create a kite-2 from centrosymmetric materials?
That's a question a little bit out of topic, but it is a good question. And so I believe so. I did some work into that, and we have to keep looking into that. It's a little bit on my very, very long to-do list. To look into that at some point, but I think it does. The question is there is going to be a kite-2 if you're changing the centrosymmetry of the crystal by straining it. The question is, can you strain it so hard to get a decent value of kite-2, and how do you do that without having to have a very high voltage or something in there, right? So I think there are ways around these things, but no one has really shown this. But people try to do that with silicon nitride overlays. I don't know if you're familiar with that work.
Yes.
And there was a huge confusion over where was the kite coming from. And I think it ended up being that it's actually not from strained silicon, but it's actually from the interface with the silicon nitride that is playing. So there are some charges in there that can introduce some sort of kite-2-like effect. But yeah, it's a good question.
How fast is the MEMS phase shift versus the thermoltic?
Good question also. So thermoltic phase shifters are, depending on how they are designed, they are in the low kilohertz speeds. With MEMS, we usually routinely get to the megahertz. They are still not very fast. This is not a modulator. You're not going to be able to modulate signals at gigahertz speeds with this. I've tried to design MEMS for gigahertz speeds. It's not easy. You have very tight geometrical constraints for that, which you cannot find in foundries and so on. But so the idea is to use this, basically to really use MEMS for what the thermo-optic phase shifters have been used to, which like today, these large photonic circuits, they are mostly thermo-optic phase shifters. You can have modulators next to it, and those are going to be very fast, and you're going to tap into them and use them. But most of your active components are phase shifters by like orders of magnitude. So if you can just get rid of all of those and get something that consumes low power, and actually it can be some orders of magnitude faster also, which is always good to be a little faster. You can do that, but there's a reason why I say always reconfiguration and not modulation, because speed is not the key aspect here. Always good to be faster, but it's not the key aspect. Do we have any more questions about this? This part. This is my first third of the talk, in case people are getting sleepy already. Yeah.
The other methods of phase modulation, phase shifting besides MEMS and.
Yeah, there are quite a few. So let's see. So one that is actually many people in this institute here are also working on is electro-optic tuning, like lithium niobate and so on, the group of Xiang, Lin, and so on. That one can be very fast for modulation, like the question I was getting before. The issue with all those effects is that they are very weak. So they are good for certain things, but for phase shifting, which you need to go up to 2 pi phase shift to reconfigure, basically change the, say, like the amplitude of a beam from like 1 to 0, depending on switch completely. You need to make very long modulators for that, very long waveguides. That's then the issue of scalability and the bottleneck changes place from power to the footprint. So there is somewhere in between there. Then people have worked also on liquid crystals quite a lot. There's quite some good work on liquid crystals for that, and that usually involves making chips, for example, in foundries, and putting liquid crystals on top and using these very large birefringence on liquid crystals to change the phase of a wave. Those can be quite efficient. They're also very slow, and they are a little bit problematic in terms of long-term stability and so on. So it's a little unclear. I think many people are still working on that, so maybe there is something else. Yeah, and then you have some other effects like carriers and so on that tend to couple phase to absorption, which is not great for most of these applications in which you want to have pure phase shift and not introduce losses every time you're phase shifting. Yeah, I would say those are. Okay, we have no more questions. I will keep.
I do have one question online.
Now I'm going to talk about combining reconfigurable photonics with detectors, with single photon detectors. You can see where I'm getting in here. So we can have this very amazing chip that we have now. We can make with MEMS now of 10,000 phase shifters. Actually, this was, again, thinking about thermo-optic phase shifters. We think about 10,000 thermo-optic phase shifters inside a chip, inside a cryostat. Again, we were going to have 2 fridges dissipating heat inside a cryostat. The cryostat is not going to do anything. It's probably going to break it. So this is particularly hard for the best single photon detectors that we can get nowadays. And those are superconducting nanowire single photon detectors, or SNSPDs. So these detectors, the way they work is you have a superconducting wire. So it's very thin wire, and it's meandering on your chip. Then you drive a current through this wire while it's superconducting. So again, no power dissipated in there. And you drive the current close to the critical current of the wire and the superconductor, in a way that when you get a very small energy increase that can be due to a photon hitting your wire, it's going to switch from superconducting to normal metals. And when we switch to superconducting to normal metal, you get the pulse on the voltage of your current that you're sending through on your circuit. And then you can use that pulse as the signal that has told you basically that you have a single photon hitting your wire. So these are very good single photon detectors. You can buy them nowadays. They are, of course, superconducting, so you need to have a cryostat, but they have shown up to more than 98% detection efficiency. So extremely good detection efficiency, very low jitter, which means that they can provide extremely tight timing accuracy, so sub 3 picosecond timing accuracy. so extremely fast detectors. They have also been shown to provide photon number resolution. So you can measure not only single photons, but also if you have 2 photon states or 3 photons or 4 photons, you can actually detect them also with these wires. And also short reset time, so you can measure high count numbers with these or photons spaced quite tightly. So in this case, what we want to look at is, okay, we have demonstrated that we can have MEMS reconfiguring photonics. And of course, we cannot have thermo-optic phase shifters to reconfigure photonics that we have next to superconducting detectors inside our cryostat. So what we do is let's see if we can combine them and they actually work together properly. So if we indeed do not dissipate heat so that we don't perturb the superconducting nanowire, because they are, again, extremely sensitive to heat. So the device we came up with looks like this. So what we have here is 2 input grating couplers, a little bit funky looking grating couplers. They are designed for objective coupling. We have laser lights, or actually single photon lights, coming into one of these gratings, and then it travels through the waveguide. In this case, our silicon nitride waveguide, not silicon, like before. And these waveguides are going through a directional coupler. So these are 2 waveguides that have the same geometry, and they are very close together. So they are effectively coupled, which means that if you send photons here in one of these waveguides, they're going to be like bouncing back and forth between those 2 waveguides as they travel through this coupled system. And then depending on the geometry of this directional coupler, you're going to get the photons coming out in one of these arms or the other that they're connected to superconducting nanowire single photon detectors. And of course, because we can change the geometry of the directional coupler now with MEMS, we just put a MEMS cantilever here. So we can change this geometry. So we change the coupling coefficient so that we can actually have a switch that basically switches between light going into one of the superconducting detectors or the other superconducting detector, right? This is on the same device, on the same chip. And this cantilever is made with the superconducting material that we are using for the nanowires. So we fabricated this device and we tested it, and this is what we see. So we have, we are looking at the counts on the SNSPD. So these are on the detectors on the chip. And we are having tuning the voltage of this MEMS. So we start with most of the light in detector A. And as we increase the voltage, we are changing the geometry, we are changing the coupling coefficients, and we see the light from detector A going down, the light from detector B going up, and so on and so forth, which is fitting our simulations. So we see that indeed it works, at least at DC voltages here. So we see that as we increase the voltage in the MEMS, we see the change in the counts from detector A to detector B. So what we observed was a 28 dB extinction ratio with up to megahertz operation, which is limited by the MEMS resonance frequency. So then we went on and we decided to check some of the applications that this could be useful for. So one of the things that we looked at is on-chip power stabilization. So now we have a way to tune the power that goes into our detectors, the power that goes into our circuit by using a MEMS directional coupler, so a tunable directional coupler. And stabilizing power on a chip is very important for a lot of applications, in particular for quantum applications, when you want to have your pulses going into your single photon emitter, and you want to make sure that you have the right power going in there so that you can excite it with the right power to excite the single photon emission process from it, for example. So this is, if anyone has worked with coupling into chips, it's also very problematic, all this stability, because anytime you have a waveguide, a fiber coupling into your chip, you can have vibrations coupling, you can have fiber laser instabilities coupling into your chip, and all these things will make your power fluctuate. So what we did here was a pretty simple experiment. We take our device, the one I was showing you before, with the 2 detectors and the MEMS directional coupler. We attach one of these detectors to a PID loop that we feed that back into the voltage source of the MEMS. So what we see is that if we increase the power that we send in and we use this PID loop to stabilize the power on this arm, we can achieve below 1.3% power stability over 12 dB range, which is a huge range. So this works, simple experiment. We went on and decided to check if this device, now that we have a tunable directional coupler here with the 2 detectors, we can use it to enhance the dynamic range of the single photon detectors. And that is because single photon detectors are super good down here when you have very low powers, when you have single photons. But as you increase the powers, there is a point in which they start saturating when they cannot measure single photons as fast. So up here, when you reach these powers, they start saturating. So you don't measure something proportional to your power. So what we do here, we start with the device as we fabricated it with no voltage in this case. So most of the light is going into this detector, the orange detector, which actually happened to be, we had a little different efficiencies in our detectors because this one had a fabrication fault, which actually we use in this work, in this experiment. So this one came out with lower efficiency and this one with higher efficiency. So we start getting all the light in there. And then as the orange detector starts saturating, we basically switch the MEMS into the other detector. Because it has lower efficiency, it has more losses. We can keep counting photons, so we keep increasing power. And then when this one is near saturation, we actually switch again into the detector orange, but in this case, we actually measure with the green detector. So we have very little power going into the green detector, plus the extra inefficiency of the green detector. So we achieved up to 90 dB, more than 90 dB dynamic range, which is pretty large dynamic range for a detector, for a photodetector that actually goes down all the way down to single photons. Then after this, we went on to look at some quantum optics. And in this case, what we had was a quantum dot, a single photon source that was in an external cryostat. And we sent that light into our chip, into our device. So the first thing we looked at is lifetime measurement. So for the people that are not familiar with what these kind of measurements are, so we have our single photon emitter. You can look at this schematic here. We have our single photon emitter presented with this orange dot with the arrow, and we are sending in laser pulses. These laser pulses are coming from a pulse laser. We know how these pulses are, and we know that we have a trigger signal from these pulses. So then when the pulse hits the single photon emitter, it's going to emit a photon, and then we're going to be capturing it with detecting it with the single photon detector here. In this case, the black one is a commercial single photon detector. So because we know how these pulses are, we can actually time the arrival of these photons and get statistics on what's the photon time temporal distribution. So how these single photons look like if you look at it in a temporal plot. So they look like this. This is what we expect actually from these devices. And we measured this also in our chip, which is the purple line here. And you see that it fits pretty nicely. The commercial detector is a little bit more noisy because of our extra loss of coupling into the chip, because our coupling was pretty inefficient. And yeah, the lifetime measurement was what we expected from these quantum dots. So like 232 picoseconds. And then we went on to measure if we have indeed, we want to confirm that we have actually single photons on the chip. And we do that by looking at second order autocorrelation measurements. So again, if people are not familiar with what that is, I have a little explanation here. I just wanted to show you first here, because I don't have a lot of space in this slide, how it should look like. So this is actually with two detectors outside of the chip. What you have is, there's a delay time here. Then I'm gonna tell you what it means in a while, but you see here pulses that are periodic. And then there is, when this delay is 0, you see that there is no pulse, there is no peak. And then they continue again. So the way this measurement goes is we have a single photon emitter. We are sending in pulses of light. This means, again, we get single photons coming out, and we send it through a beam splitter that will split 50-50. And then these photons, one of these arms goes into a detector, the other arm goes into another detector. And we look at correlations between these detectors. Why do we look at that? Because we know that if we have single photons, we can never measure 2 clicks at these 2 detectors at the same time, because they're going to go either on one side or the other side, but never both, right? Or at least when you measure them, they collapse into one of them or the other. So this means that when these delays, so when the distances in here that we measure here in time are 0, so it's the same length here, then we should be measuring 0 correlation counts. Is that clear? So again, I was showing you behind here how it looks with external detectors. And in this case, we used one of the on-chip detectors and an external detector to look at our G2, second order autocorrelation. And we see that in 0, so when we have 0 delay, we see that this peak disappears. And in this case, it's 0.11 which is limited again by our noise because of our poor coupling into the chip. But we see that there are indeed, if this is below 0.5, we have single photons on the chip. So we have indeed single photons on the chip. Right. So just to summarize from this second third of my talk, this was actually the first time anyone has shown optical switches with single photon detectors on the same chip. So, and this was enabled by the fact that we can get MEMS in there that actually don't dissipate heat, so you can put them together with superconducting single photon detectors. I think a little bit of water. I go for the last part. Does anyone have questions about this so far? Yeah.
How much efficiency have you been able to get for the on-chip SNSPDs? And what kind of timing resolution do you have for these?
Yeah, so these ones, they were, because they were homemade in this process, they were not as good as the ones that you can buy. So in terms of efficiency, actually, we didn't fully characterize the efficiency of this. And we know that the internal efficiency is very good. It should be unity. Internal efficiency meaning like if a photon hits the actual detector, then you actually get always a click in there. And that comes from the fact that our detectors are saturating. So we measure if we sweep the bias current and we see it saturating, we get unity internal efficiency. The issue is that in our chip, there are a lot of extra losses through, because again, it was a very in-house kind of, I had a few months to develop this process without any help. So the waveguides themselves were lossy, and that adds to the efficiency. In terms of jitter, they were in like 100 picoseconds jitter.
That's fairly good.
So it's decent compared to what you can achieve with SNSPDs. It's like another magnitude worse than the kind of state of the art of really optimized SNSPDs. Yeah, that's what we were getting with this. There's a lot of details, of course, on like how do you process this to be better. But even the idea of this work was to just show that you can actually do switching with SNSPDs. Optimizing the SNSPDs was not the goal. Yeah.
So I have a question from Wayne Knox, who's online, having to do with the MEMS switches.
Yeah.
I'm going to go in reverse order. What's the lifetime of the MEMS switches?
I'm not sure what they mean with the lifetime.
I think he's referring to reliability, but Wayne, feel free to unmute if you want to explain that.
Okay, in the sense of how many times you can switch them until they...
What's the expected lifetime?
Yeah, so we basically tried many billions of cycles without seeing any degradation. We have our AC measurements that I don't show here of like megahertz were there for very long. So we have data showing that they can last many billions of cycles. And particularly for these kind of MEMS that are no contact MEMS. So in these devices, we never have any physical contact. And that can be problematic in MEMS because every time you have physical contact with anything like electrical switches, MEMS electrical switches, you are actually degrading your surfaces all the time. Basically, right, you're kind of fusing together and separating things. In this case, because we can rely on evanescent field interaction, we don't need to have contact. So we actually don't touch the surfaces at all. They are always the same. So in that sense, there is no degradation that we can see. And particularly for single crystal silicon, like we have in here, many of the single crystal MEMS devices, they work for many billions of cycles regularly.
So his other question was, how much power does the high voltage MEMS drive or dissipate?
Yeah, well, dissipate, we can see that it works with the SNSPD. So here because again, this was very unoptimized. And in this case, we had some strain issues in the material. We have to go up to 300 volts. And at 300 volts, the SNSPDs are still working. That means that...
Yeah, I guess his question was, you have to supply that voltage from somewhere.
Yeah.
And when you factor in the energy cost.
Yeah, right. So the dissipation on the on the cryostat is near 0 because the SNSPDs are working. The dissipation outside of the cryostat is pretty high. I agree. The thing of this is that this is not fundamental. So like what I have shown before, these devices were working at an order of magnitude lower voltage. We can bring this down an order of magnitude more. It's just a matter of how you design your geometry and what speeds can you tolerate, and what kind of geometry you have access to also from if you are doing it in a foundry or if you're doing it on your own. Okay. So I'm aiming to get this down to the like 3 volts or 5 volts level. Yeah.
Okay. Cool.
Yeah. What source were you, what source were you using to test the second order degree of freedom?
So that was quantum dot single photon sources that we had from a collaborator in a different cryostat. So those were, I think they were gallium arsenide quantum dots at 895 nanometers from Armando Rastelli in JKU Linz. They are growing very nice quantum dots there, and we had a long collaboration with them in the group of, this was done in the group of Walswiller with Klaus Jones. All right, we have no more questions. I'll go for the last part of my talk, which deals with sources, and in particular, single photon sources in photonics. So a little bit back to motivation. We all like silicon photonics. We know silicon photonics is great. And particularly for quantum photonics, it really has most of the things that you want to have on a photonic chip. So you can make very nice waveguides, you can make very nice delay lines, splitters and couplers, filters, cavities, fiber to chip interfaces. So you can just come in with a fiber or whatever to couple into your chip. We can have some pretty good modulators. And I have shown you in the previous 2 sections of my talk that we can actually make phase shifters in a foundry with MEMS that are cryo-compatible and single photon detectors compatible with these phase shifters. So, and of course, we know that electronics are great in silicon. I hope I don't have to convince you of that. So what's missing is if we could have monolithic single photon sources and quantum memories that are compatible with all these components, because if we have that, then we can really have a great toolbox there to basically do everything we can dream of with quantum photonics. So one of the, in particular, from quantum mirrors and quantum memory, something that is very attractive is these artificial atoms in the solid state or color centers. So these devices, they have shown very long coherence times. So you're basically coupling spins to optics, and you can have in these spins very long coherence times. And because you're coupling spin to optics, you can have efficient spin optic interfaces. They can actually store information or have stored common information within optics and spins. And because they are in the solid state, they have prospects for scalability, because you can potentially, these are single atomic defects in solids. They can, you can potentially have many of them. You know how to make them properly and put them on the chip properly. So this has allowed quite a lot of technological demonstrations that have been really breakthroughs in the field. I'm showing here 2 of them. The first one was by the group of Misha Lukin in Harvard. They showed that they could break the repeaterless bound for quantum communication. So by using a quantum memory here, this is a diamond color center inside a cavity inside the cryostat. They could actually make break the repeaterless bound of quantum communication. So they can actually make a quantum repeater with a higher rate than you can ever do with single photons without any memory device. Something else, the group of Ronald Hanson in TU Delft, they showed that using these quantum memories in diamond, you can actually make a 3-node quantum repeater. That was the first time that was demonstrated. So you can actually share information and teleport information within these 3 nodes in different parts of the lab here and now in different cities. So these are all enabled by these artificial atoms in the solid state. Also, there's a lot of protocols there that one could use these for quantum simulation and quantum computing and sensing that are very exciting prospects. Now, an issue with these devices is that the current material, which are diamond, silicon carbide, they face quite some stringent limitations. And those are that fabrication complexity. Fabricating in diamond is pretty hard just because of the substrate that you have. Makes things very hard. You don't have a substrate like a silicon or insulator substrate. So you have a very hard time making nice cavities to enhance light matter interaction. And you cannot have easy large scale integration of these devices. And on top of that, the operation wavelength of these materials lay in the visible range. So if you want to send this into your fibers, into your from going from lab to lab or city to city, you will need to frequently convert this light into telecom light so you can send it through those fibers. And that is very noisy and very problematic so far. So those are stringent limitations, and we are hoping to fix that by actually changing material platform. So very recently, people have looked at single artificial atoms in silicon. So again, color centers that were isolated in a silicon, in this case, silicon host. You have carbon-related color centers that you see here in this plot. This is by the group of Guillaume Casabois in Paris. And they were the first in isolating single color centers that are carbon-based. So again, you see the spots. If we look at the photon statistics here, you see, again, a second-order autocorrelation measurement showing single photon emission and operation in the telecom band, which is pretty exciting. So now you can have actually artificial atoms in silicon, so great material for making devices out of it that operate in the telecom band already. So this was taken a step further by the group of Stephanie Simons in Canada, and they showed that with one of these color centers in silicon, you can actually have spin optic interfaces. So you can actually have it has a ground state spin, and you can see how, depending on the spin, you have different optical transitions here. And this was actually published in Nature recently, so I have to change that link. So what we did here, we decided to go into this field because this looks very exciting. And we started by looking at, okay, can we actually couple these color centers into waveguides? We know that for some of these color centers in diamond, if you put them in waveguides, they degrade very heavily. So would that be the same in silicon? Will we actually be able to see them in silicon photonics, in silicon waveguides? And we did that basically. We implanted this actually commercial standard SOI, standard silicon insulator that you can just buy. We implanted it with carbon. We did all the processes to fabricate color centers in the single color center regime. And then we are exciting here from the top. These are actually G centers, which is just a name for these color centers in particular. They are based on 2 carbon atoms on the silicon interstitial. We excite with green light from the top with a confocal microscope. And the infrared light that comes from these artificial atoms couples into the waveguide. And we look at it inside a cryostat with a lens fiber on the edge. We see the O-band zero phonon line here. You see this peak, meaning the emission in the telecom band. I'm showing here a little bit of the energy levels of these artificial atoms. And we show single photon emission. So what we first did, actually, let me show here the chip. So in this case, very simple chip, just waveguides looping back into an edge. And we have an edge coupler here. We have our fiber coming in through here. So we couple the light that comes out of this waveguide. And again, from the top, we send in green, we scan through. And when the green hits the waveguide and the spot that has a color center, it will emit light into the waveguide and couple out into our fiber. And this is what we are measuring here, what we are plotting here. So you see that when we scan through, we see only the waveguide and we see only spots in the waveguide. So that's very exciting. Then you are actually, these individual spots means that you actually have some sort of, discreteness in there, which is potentially single photon emitters. So we looked at statistics of them. So we see very narrow lines in each of these spots, and these narrow lines, and if we plot many of them and we look at the statistical distribution of them, we see what we call an homogeneous distribution. So how separated are they with each other? This of 1.1 nanometers. This actually happens to be an order of magnitude narrower than what people have seen in these bulk samples, in the first samples that the French group was reporting on. It's still a little bit unclear of why. We have some theories, but we see them being basically closer together than what people have shown before. Then we went on to measure our second order autocorrelation measurement, similar to what I was showing you before. We want to see this peak going down here at 0, below 0.5. And even if our system is very weak and kind of lossy, we still see this dip going all the way down below 0.5. So we have indeed single photons coming out of these systems, again, on the waveguide, on a silicon photonic waveguide, a single color center. And then we also looked at some lifetime measurement to basically confirm that this is the same, or at an extra layer of confirmation that this is actually the same system that people have been looking at, these single G centers. So just to summarize from this part, this was the first time that anyone has shown artificial atoms in silicon photonics, so really monolithic in silicon photonics. I would add here single artificial atoms, so like single photon emitters. And I will actually just go to conclude. We can then ask questions about this part. I would like to conclude by saying that we have developed scalable building blocks for classical and quantum photonics. So I have told you about ultra low power, boundary scale, reconfigurable photonics that use MEMS. And the combination of those with single photon detectors, actually they work nicely together, as you can see. And again, this was achieving more than 5 orders of magnitude lower power consumption than the thermo-optic traditional phase shifters. And moreover, we have shown that we can actually get artificial atoms in silicon photonics. So we can actually combine these platforms to do something very exciting, which is what I'm planning to do in my position in Delft. And if you're interested in working on these topics and you're looking for a couple of years in Europe, feel free to write to me. I will have PhD and postdoc positions available that I'm starting to search for now. Delft is a nice city and with a nice campus and with very good people in there. So it's exciting times. And there's also a lot of nice funding for quantum and photonics. So there's a lot of things to do. I would like to acknowledge people that have been part of this work. So at MIT, Professor Dirk Englund and Mihika Prabhu, which were working with me, and also Lorenzo very heavily on these silicon color centers. That was a lot of very basic work we had to do to get that working. People from KTH, my advisor, Kristin Gilfason, and Val Swiller, Klaus Jöns from Paderborn, Armando Rastelli from Linz, people from the Morphic project, and my funding. Also, if people are interested in like talking later about some other work, I'm just throwing in here some other work that I have been doing. Maybe some of this is familiar to you. So we were using MEMS for a few other ideas that I had in my PhD. So for beam steering, we were using MEMS for nonlinear photonics to change the dispersion of ring resonators to improve nonlinearities. We were using suspended photonics for mid-IR sensing of gases. That was pretty cool. We did some 2D material single photon emission into silicon waveguides, silicon nitride waveguides, and some polarization components. So with that, I would like to thank you and happy to answer your questions.
I know there are a couple of questions I can ask before, but they left. Actually, there was one that Wayne had asked before online. For your intended applications, how fast do the phase shifters need to be?
Yeah, so what I was mentioning before, I had a similar question before. We want to use them basically as the thermo-optic phase shifters are used nowadays. So we are okay with them being slow. We are happy with some kilohertz of speed, basically not to have to wait too long during reconfigurations, but these are not modulators, these are reconfigurable photonics. So you just want to tune your phases so that you get your circuit to start in the right position, and then you can do your signal processing. So in that case, like the MEMS that I have been showing, they go up to the megahertz speeds, which is definitely fast enough for this application.
And my question was, so on the single photon emitters, so you're coming in right now, you're coming in with a green light.
Yeah.
And of course, the absorption depth for silicon in the green is much longer than, say, the thickness of the waveguide.
Yeah.
Any ideas on how to, within the integrated photonic geometry, how to more efficiently excite them?
Yeah. So what we want to end up doing is to do resonant excitation. So, and that's something we are working on as we speak here. We are trying to do that resonant excitation. We have also, I mean, we have some of these very beautiful foundry work that we can have silicon nitride and silicon in the same foundry, right? Like in photonics, which is great. Or if we happen to need to use visible wavelengths, in principle, it may be okay just with resonant excitation if things work as we expect. But yeah, we are still on the physics side of things here, try to understand a little bit more the physics of the defects. So, yeah.
Did you mention more specifically the color center you used or the artificial, what the artificial is?
Yeah, so we are looking at G centers. So 2 carbon atoms and a silicon interstitial within the silicon lattice. Yeah.
It's the 400 chemistry using this millimeter and what it ideal 400 integrated.
Yeah, so you want to have them as fast as possible, right? You want to be to increase your rates as much as possible. In this case, we actually are seeing that these devices are pretty dim. They are dimmer than what people have reported before. So I don't know if we have some issue with our material or there were some issues with like reporting or something. We are getting in the orders of like some tens or like without losses, with a very lossy setup, we are getting in the order of like some tens of thousands of counts per second. You want them to be in the millions and like as fast as possible, basically. These things you can increase by putting them into cavities. So by the Purcell effect, and that's something we are doing also. So if you put them into cavities, you can drastically increase this by orders of magnitude.
And align the single voltage to make them have the same input between.
Sorry again, you want?
I mean, do you need to align the single voltage to make them have a specific timing interval between the voltages?
Align the single photons, or are you talking about the meters? Or
yeah, for the meters. I mean, for the photons emitted by the.
Yeah, so the photons emitted by the meter, if you do like, if you have deterministic single photon emission, that's determined by your pulses, right? So if you have a pulse laser, you're gonna get a single photon every time your laser hits the meter. In reality, because you have all these losses, then you are skipping some of these. And depending on what you want to do with them, let's say if you want to interfere an early and a late photon and so on, you may want to, it may be problematic if you don't have high rate, because you will have to wait longer. But yeah, in principle, when you put them in a cavity and you get them bright enough to get this deterministic single photon emission, then it's good.
Is that the G2 you measured, is that typical for G centers or are they have they been lower? I was just wondering if that's like the G2 specific to the system that you're using.
No, the G2 is specific to our very low counts in our system. So all these things are noise. Or the fact that it goes only up until here is because of background, because we have to integrate for very long. If you have higher counts, if you put them in a cavity, you can get this much cleaner. It's just a matter of background. As long as it goes below 0.5, you have single photons, and the rest of it is basically extra noise that you're adding to the system, extra background you're adding. So people have shown like cleaner spectra from free space coupling. It's still unclear the dipole orientation of these centers with respect to the out of plane. So we actually don't know if that is a problem in terms of like coupling into the waveguide. Maybe it couples better, let's say like a TM polarization or something. And in our case, our waveguides are leaky for TM. So we are actually losing that line.
I think Joe Everly had a question.
Joe, your turn. Okay. All right. So I had a question on dynamic modulation. Is MEMS fast enough to induce something like adiabatic frequency conversion in device? It's not fast.
No, it's a megahertz range, so it doesn't really.
And could it be used to change the lattice constant dynamically of a photonic crystal device?
Yeah. I mean, but it's gonna be slow, right? But so it's definitely, you can use it for tuning things and aligning things in place, which I think it's is one of the main problems that we're facing nowadays with a lot of these quantum systems, that they come out very random, and you need to align spectra, align cavities, again, tune up your circuit. For that, I think this is great because, again, you run it in DC, there's no power consumption, everything is nice, at least, yeah, in your cryostat. So for modulation, I think you're better off going to a proper electro-optic material that you can actually get some cheap.
I think I missed it, but how do you implant the G filters in the silicon bed?
So we actually, I think, I have, oops. Let me go back here. Okay, anyway, this is easy to say. I think I have it somewhere in my extra slides. We do carbon implantation on a commercial ion implantation company. And then we do annealing in-house. We have to anneal at 1,000 Celsius with rapid thermal annealing. This actually recipe has been shown already. It's not something we came up with. And then we do processing of the photonics. Yeah, pretty simple.
G2.
Sorry, there?
How long did you collect data for G2?
That G2 was headache. Yeah, it was problematic. It was very long.
How many days?
So one issue that we had in our system was that it was drifting over time. That which made this actually much more complicated. So we had our let's see. Basically, our green light was drifting a little bit overnight. So it was quite annoying. So we had to. I think we integrated. I think for like 2 nights or something. And I think it was not too bad. It was just the fact that it was drifting. If it would have actually stayed in place, it could have been something of a few hours experiment. But it was drifting overnight. So we didn't find a really good way to bring it back to the right place. We tried a few different things, but yeah, I think this is just a matter of having a better coupled system, which we are looking at cavities now to do that, and there is less problems.
How strong is the coupling strength of between your atom and your waveguide? Can you break the rotating wave property?
Yeah, so this is very well. First of all, we don't know, like we back calculated something, but because the counts are so low, like small changes in your efficiency measurements before can actually affect your results very largely. So, and also we cannot separate quantum efficiency from coupling, right? And something that we have seen is that it looks like the quantum efficiency of at least these guys that we are looking at, these G centers, seems to be pretty low. So that means that we cannot know between those two things. So we don't know how well the solar center is coupled into the waveguide. We only know a combined measure for quantum efficiency times inefficiencies in coupling. I don't remember exactly what we achieved. It's in the paper, so it's on that archive paper. If you're interested, it's in the supplementary. We had some calculation of that, but it was pretty low. It was like in the 1% or something range.
All right. So I think let's thank Carlos again.
Yeah, thank you a lot.
Thank you very much.
Yeah, thanks for inviting.